Let's examine two systems, non-rectangular versus rectangular. As you can see, there are two parallelograms. The one on the right is a very special one because the two components create a right angle, meaning the angle between our x and our y, which are the two components of the resultant r along the x-axis and along the y-axis respectively, is equal to 90 degrees, therefore creating a rectangle, thus the name rectangular component system, as opposed to the angle between the two components of the system on the left is not equal to 90 degrees. Therefore, this type of system is called non-rectangular. I'd like to point out that each parallelogram is of course made up of two identical triangles. Here is the first triangle for the system on the left, and the second triangle that is identical to the first one is of course just right above it. The same is true for the rectangular system. It is again of course made up of two identical triangles. Here is the first triangle, and the second triangle that is identical to the first one is again just right above it. Let's examine the non-rectangular system first. Before I introduce to you two very important laws, I'd like to define some angles. The angle that is opposite of F1 in this bottom triangle, since the non-rectangular system as well as the rectangular is made up of two identical triangles, it does not make any difference which triangle we examine. I'd like to examine the bottom one. The angle that is opposite of F1, the angle that is opposite of F1, I'd like to call that alpha. The angle that is opposite of F2, let's call that beta. And the angle that is opposite of the resultant, let's call that gamma. And of course, gamma is not equal to 90 degrees. The first law is called law of sines. And you may have heard this in your physics or in your math classes. The law of sines is an equation that relates the lengths of the side of an arbitrary triangle, in this particular case F1, F2, and the resultant, to the sines of its angles. Well, let's make this a little bit more concrete. There are three sides. I will choose F1 first. F1 over the sine of the angle that is opposite of F1. The angle that is opposite of F1, well, that's just alpha. And notice that I don't have a vector sign above F1 because I do not want F1 to be in its Cartesian vector form. I do not want F1 in terms of ijk. I only want the length or the magnitude of F1. So according to the law of sines, F1 over the sine of the angle that is opposite of F1, that is equal to another side in that bottom triangle, F2, over the sine of the angle that is opposite of F2. The angle that is opposite of F2 is beta, and that's equal to the third side in that same triangle, which is of course the resultant, over the sine of the angle that is opposite of the resultant. Well, that's just equal to gamma. So again, this is an equation that relates the lengths of the side of an arbitrary triangle to the sines of its angles. The second law is called law of cosines. And again, you may have heard this in your physics or in your math classes. We are still examining the bottom triangle. F1, F2, and R are still the three sides. I will start with F1 first. F1 squared, according to the law of cosines, is equal to R squared plus F2 squared minus 2 times R times F2 times cosine of the angle that is opposite of F1. The angle that is opposite of F1 is alpha. There's a very easy way to remember the law of cosines. There are three sides, of course. Just choose any side. In this particular case, it's F1, and place that on the left side of the equation. The other two sides should be on the right side of the equation. Let's try writing the law of cosines for F2. Well, F2 squared is equal to, I am placing F2 on the left side of the equation, therefore the other two sides, which are the resultant and F1, should be placed on the right side. So therefore this is r squared plus f1 squared minus 2 times r times f1 times cosine of the angle that is opposite of f2. The angle that is opposite of f2 is beta. Finally, the third side in that bottom triangle is the resultant, and according to the law of cosines, r squared is equal to f1 squared plus f2 squared minus 2 times f1 times f2 times cosine of the angle that is opposite of r. The angle that is opposite of r is gamma. Are we able to express law of sines and law of cosines in the rectangular system? Most definitely. Before we do that, why don't we define some angles? I'd like to define the angle that is between the resultant and the x-axis as theta x. I have chosen this notation intentionally so that it'll be easy for me to remember that the angle between the resultant and the x-axis shall be called theta x. Notice that the subscript is x. It makes it easy for me to remember that is the angle between the resultant and the x-axis. I'd like to define another angle and call it theta y. This angle is the angle between the resultant and the y-axis, and I'm using the same pattern as I did for theta x. Theta y, I've chosen the subscript y intentionally so that it's easy for me to remember that is the angle between the resultant and the y-axis. Okay, why don't we start with law of cosines for the rectangular system. I am examining the bottom triangle. 3 sides, of course. I'll start with Rx. Rx squared is equal to r squared plus ry squared minus 2 times r times ry times cosine of the angle that is opposite of Rx. The angle that is opposite of Rx here is Rx. In that bottom right triangle, the angle that is opposite of Rx is just this angle. Well, this angle is equal to theta y because they are alternate interior angles. So therefore, the angle that is opposite of Rx is just theta y. How about the law of cosines for another side of that same triangle? Ry squared is equal to r squared plus rx squared minus 2 times r times rx times cosine of the angle that is opposite of ry. The angle that is opposite of ry is just theta x. Finally, the third side in that same triangle is the resultant. According to the law of cosines, r squared is equal to, remember, you just place a sign on the left side of the equation, the other 2 sides should be on the right. So therefore, r squared is equal to rx squared plus ry squared minus 2 times rx times ry times cosine of the angle that is opposite of the resultant. Well, the angle that is opposite of the resultant in a right triangle is always 90 degrees, and cosine 90 is equal to 0. So therefore, the third term on the right side of the equation for this law of cosines is equal to 0. And as you can see that the law of cosines for the resultant has cascaded into the Pythagorean theorem. How about the law of sines for the rectangular system? Again, I'm still looking at the bottom triangle, of course the same 3 sides. I'll start with Rx. Rx over the sine of the angle that is opposite of Rx. Well, that's just theta y is equal to Ry over the sine of the angle that is opposite of Ry that is theta x, and that's equal to the third side in that right triangle, which is the resultant, over the sine of the angle that is opposite of the resultant. In a right triangle, that's always 90 degrees, and sine 90 is equal to 1. So therefore, this third term is just r over 1, which is equal to r. I'd like to define for you two more definitions in rectangular system. The first one is direction cosines, and the next one is direction angles. I'll start with cosine theta x. Theta x is again the angle between the resultant and the x-axis. And by definition, cosine is adjacent over hypotenuse. If you look at this bottom triangle, the side that is adjacent to theta x is our x, and the hypotenuse is, of course, the resultant. So therefore, by definition, cosine theta x is equal to rx over r. Or, if you're interested in just theta x, that is just equal to r cosine of rx over r. How about cosine of theta y? Well, cosine of theta y is this angle, and the side that is adjacent to theta y is ry, and by definition cosine is adjacent over hypotenuse, so cosine theta y is equal to ry over r, or if you're interested in just theta y, that is equal to r cosine of ry over r. I hope you see there is a pattern that is emerging here. If we are interested in the cosine of the angle between the resultant and the x-axis, well, we better make sure that we have the x component of the resultant and the resultant itself. Again, if we're interested in the cosine of the angle between the resultant and the y-axis, we better make sure that we have the y component of the resultant and the resultant itself. If I were to extend this to 3D, cosine theta z, which is the angle between the resultant and the z-axis according to the pattern, all I need is the z component of the resultant over the resultant. Or if I'm just interested in theta z itself, then that's just equal to r cosine of rz over r. And this fits well with the pattern that we have for cosine theta x and cosine theta y. The subscript is z, therefore I need the z component of the resultant, and I need the resultant itself. There is a very special name for the cosines of the angles between the resultant and the three major axes. It is called direction cosines, as opposed to the angles between the resultant and the three major axes. This is called direction angles. And what are they used for? Well, they're very important in forming direction cosine matrices to express a known vector in a different basis, which you will have more exposure to in your future math and engineering classes. However, I'd like to point out that it is always the case for this type of system that the sum of the squares of the direction cosines, well, that means cosine squared theta x plus cosine squared theta y plus cosine squared theta z. So the sum of the squares of the direction cosines of any resultant vector, that is always equal to 1.